All right. Good evening, guys. How you
Hi there.
doing?
Hey
Well,
there.
good evening, everyone. Thank you for joining us tonight. And I'm Rich Ozer, and Gerald McKeegan and John Curry are here, and they're waving away at us. And I want to thank you all for attending. I want to put a shout out to Fremont Bank, who has been a generous sponsor of this program and others here at the Chabot Space and Science Center. And I want to thank all of you who have donated in the past and have donated tonight. Our donations from the community keep our STEM programs going and keep programs like this and others going week after week. And we really appreciate your support. If you're on Facebook, you can donate to the Chabot Space and Science Center by looking for the little coin button with the heart. And otherwise, please visit the chabotspace.org website, in which case you can learn about membership and donations as you see fit. All right, well, tonight it's cold, and so we're all bundled up here. Also, our humidity is about 80%. Is that where
80,
we're at, John?
82. We're at
82.
82% now.
So
So,
let's not waste any time. We'll keep it
yeah.
going as long as we could. If it hits 85%, we have to shut down because nobody wants to squeegee off the primary mirror of Nellie. And it's already a little bit damp in here. So we're going to start with the moon tonight. And
Okay.
I think, Gerald, you want to
Yep.
head on over there and I'll make sure the camera's going.
All right. So here we go.
All right, I've got to get to the share here and get the camera
So we're up here at the
pulled up.
Chabot Space
There
and
we
Science
go.
Center. We're in the observatory with our 36-inch telescope, the one we call Nellie. And Nellie is a reflecting telescope, and it's our only computer controlled telescope. So as we move around tonight, we're going to be doing it through the computer. So bear with us here. You see the moon?
I do.
All right. Let's wander around the moon, take a little tour while we have a chance, okay? So I'm going to take us up here towards the northern part of the moon. Oops, wrong direction. Okay, Richard, I may need your help a little bit to point out some
Okay.
things as we go along here.
Okay.
Um, if everybody looks near the terminator, the dark line on the left is what we call the terminator. That's the boundary between the side of the moon that is lit by the sun right now and the side of the moon that is in the darkness still. And that terminator moves every day, actually every hour, as the moon orbits around the sun. The terminator is at different angles, or the moon is at different angles between the sun and the earth, and so the terminator changes position. So right now we're a little bit past first quarter moon. Now just to the sun side of the terminator, you see a large crater with a kind of a flat floor, and that is the crater Plato right there. Plato is a crater. It's about 61 miles in diameter, and it's about 3.5 billion years old. So the impact craters that you see on the moon, most of those craters were formed somewhere around 3 to 4 billion years ago. At that time, the solar system was a much more active place. There were a lot of impacts on the moon and on the Earth, as the new solar system was still clearing itself of a lot of the leftover debris from when it first formed. So Plato is one of the older craters. Plato is at the kind of the northern rim of a large basin called Imbrium Basin. So if you look just south of Plato, you see a large kind of smooth area that's dark in color. When you look at the moon with your naked eye, you see dark patches and light patches on the surface of the moon. The dark patches we call mare, which is a Latin term for seas, And that Imbrium Basin there that you see just south of Plato, that's one of the largest seas on the moon.
Hey, Gerald,
Yes,
I'd like to point something out here
sure.
about the Plato Crater. I'm going to center this a little bit and zoom in quite a bit here. The shadows from the sun are really dramatic tonight,
Oh, they
and
are.
along the rim here,
Yeah,
Yeah,
really
and you can
cool.
yeah.
see this beautiful set of shadows here. And I don't know if there's much to say beyond that, but the advantage of viewing the moon during one of its phases, not during a full moon, is that you could learn a lot about the relief of the mountains by observing the shadows. And you can see it's not smooth. There's like these peaks, right? And that's suggestive of peaks along the rim of the Plato crater.
Right. And you can actually, if you look at the shadow, you can actually see the contour of the rim. It's reflected
Right.
in the shadow. Yeah. And then
Anyway,
to the right of Plato, well, let's just stay zoomed in right about like that. To the right of Plato and down a little bit, you see a range of mountains along the rim of the Imbrium Basin. It's called, I believe those are called the Alps. They
right.
name mountain ranges on the moon after mountain ranges on Earth. And then you see kind of a horizontal um, valley, if you will, extending away from um, the Imbrium Basin. That's called a graben. And what happened is that impact that caused the Imbrium Basin actually cracked the surface of the moon and created a couple of parallel cracks where it then slumped in between the two cracks. And so that little valley there looks like a little channel between the mountains is called a graben. Um, Now, what happened was 3.5, 4 billion years ago, the Imbrium Basin was created by a very large impact, and that cracked the surface of the moon, cracked the crust. At that time, the moon had a molten interior, and the lava oozed up through those cracks in the crust and filled the impact crater, the basin that was once the impact crater that was caused by the Imbrium impact. So that smooth area that you see there, that dark smooth area, that's lava that has oozed up and filled the basin. That goes on over several million years, and coincidentally, the impact that caused the Plato crater happened roughly the same time. So it too filled with lava from the same cracking that caused the Imbrium Basin to fill. So moving around here, maybe we zoom out a little bit, Richard.
Sure.
All right. And I want to just kind of point out a couple of other things here. Going west here, you see two craters there, one above the other. The one, the higher of the two craters is called Aristoteles, and it's a little bit of a younger crater. It's only about 2.5 billion years old, and it's 53 miles in diameter. And directly below that is Eudoxus, which is even younger still, and it's about 41 miles in diameter. We'll wander on down here a little bit. See some more craters here. This large area to the right, the large open area there, that's called the Sea of Serenity. And then again to the left of there, we go in the right direction here. Oops, that's not the right direction. So you see some more craters inside the Imbrium Basin. The fact that those craters are inside the Imbrium Basin tells us that they are younger craters than the Imbrium impact. Just identify a couple of them. The one that you see kind of at the top, there's like three of them in a little triangle. The one at the top is called Aristillus. The big one with the very smooth floor, that's Archimedes. Let's see, Archimedes is about 50 miles in diameter. It's a little bit younger than the Imbrium impact, but not a whole lot younger. And Aristoteles, which is the one up to the right of it, that one is much younger. That one is only about 1 billion years old, and it's 33 miles in diameter.
That's this one right here.
Correct. Right. All right. And then coming on down, you see that long arcing mountain range. That's called the Apennines. Again, named after a mountain range on Earth. And right at the foot of the mountain range, at the bottom left there, you see another crater. That's called Eratosthenes. A little bit down, yep, down.
Yeah,
down.
I've unfortunately got a thing in the way that's preventing me from moving my cursor any further down.
Well, just below his cursor is that crater. It's called Eratosthenes. Now we lost it.
Yeah, I know. I have to try this again here. Bear with me. Okay, let's see what's going on here. There we go.
There we go. So anyway, Eratosthenes. Yeah, Eratosthenes is named after a Greek philosopher who lived in Egypt back about, I want to say around 300 BC or BCE, depending on how you want to designate it. And he was the first one to correctly measure the circumference of the Earth. Contrary to popular belief, they knew even back 2,000 years ago that the Earth was round, that it was a sphere, and Eratosthenes came up with a method for measuring the circumference. He knew of a small town on the Nile River, south of Cairo, south of Alexandria. The town was called Syene, and it had a well in the town. And on certain days of the year, the sun was directly overhead, so it shone straight down into the well, and there were no shadows in the well. So Eratosthenes figured out that if he waited until that day and time when the sun was directly overhead in the well of Syene, if he then took a pole of a certain height, stuck it in the ground up north around Alexandria, that pole would cast a small shadow because it's far enough north that, unlike the well, the pole would cast a shadow. And by measuring the length of that shadow and computing the angle, he was able to then derive the circumference of the Earth. Now, his measuring system was kind of crude, but mathematically, it's a perfect system. So he came up with a relatively good number for the circumference of the Earth. Not exactly correct, but pretty close. So anyway, he got a crater named after him.
How far off was he?
I want to say he was about 1,000 miles off, is my recollection.
That's not bad.
There's actually some debate about that because he used a unit of measure called a stadia.
Oh, right.
And there's some debate about exactly how long a stadia is. So depending on what you agree on to be the length of the stadia.
I would say it's the diameter of the Oakland Coliseum. One stadium.
I think it was a little bit bigger than that.
Yeah.
This is back in the Greek and Roman days, and things were bigger then.
Yeah, why didn't they all use furlongs?
Yeah, that's right. Yeah, just try to keep us on our toes.
Yeah. So anyway, a little background about Eratosthenes. So what I want to do now is kind of head south. We won't spit. Whoops, that's not south.
That's north.
Yeah. One problem with using a computer-controlled telescope is sometimes what the button says.
Right, up and down really are relative.
You have to hold the keypad right side up, Gerald.
Yeah, right. So I want to kind of focus in on 3 craters that are more or less right in the middle of this image. These 3 we call them the snowman because they look like an upside down snowman. A lot of times when you look through certain kinds of telescopes, refracting telescopes, with which invert everything, this thing would be a right side up snowman. So the three craters, the biggest one at the top is called Ptolemaeus. It's a pretty good sized crater. It's about 93 miles across and it's about 4 billion years old. It's one of the older craters. Directly below that is the crater Alphonsus, and it's a little bit younger. It's about 3.8 billion years old, and it's about 71 miles in diameter. And then the smallest one, what would be the head of the snowman, that's Arzachel, and it's only about 3.5 billion years old, and it's 59 miles in diameter. So if you look at Arzachel, you'll notice that it has a little bit of a central peak, and then there's a small crater up and to the left of it that also has a central peak. Those central peaks are called rebound peaks. And so what happens is an asteroid hits the moon, and it's a pretty big impact. It compresses the ground directly under the impact point, and dissipates all its energy. It blows stuff out to the sides, creating the crater rim. And then two things happen. Number one is the compressed ground in the middle of the crater kind of rebounds back up a little bit. And at the same time, all that stuff that slid up onto the rim actually slides back down. So some of it slides back down into the crater. And those two forces produce that central peak we call the rebound peak. Now, that happens mostly with bigger craters. Smaller craters on the moon are just bowl-shaped, but the bigger ones have that central rebound peak and often have fracturing in the center and so on.
Hey, Gerald.
Yes.
Jerry wants to know if that's near Mons Morrow / Ranger 7.
Morrow is somewhere in this region here, but I'm not exactly sure where. So I know a few of these
you can
crater
say it's
names.
Somewhere near. That's good enough.
Yeah. I know some of these crater names, but I don't know all of them and all of them. Okay, so I think I'm going to go west here.
Before you leave this area, can you talk about this feature here where my cursor is?
Oh yeah, straight wall. Yeah, maybe we can zoom in a little bit on that.
Yeah, that would really be great to hear more about. Let's zoom in here.
So if you look carefully, this is really easy to see visually through a telescope. You see what looks like a straight line in the middle of all these craters and everything. There's this absolutely straight line. And it's been given the name the straight wall. And it's actually caused by the surface dropping down on the left side and being a little bit higher on the right side. So there's a cliff there, and it's a couple 100 feet high. It's a pretty good sized cliff. And that's just a feature, geologic feature that happened, again, billions of years ago, and it has left behind this beautiful straight line, which we call the straight wall. And it's one of the cool things to look for when you're, looking at the moon with a small telescope.
Yep.
And this is just the perfect time to see it because you get the shadows. All right, so wanted to kind of head off into the west a little bit here. I'm not sure. Yeah, it's
a little faded out there, but
yeah, that's the problem with looking at parts of the moon that are fully lit by the sun, where the sun is at a high angle. So you see two dark patches on the right side of the image there, and between them, just to the left, you see a crater with a central peak right there. That's the crater Theophilus. It overlaps the crater Cyrillus. Theophilus is about 61 miles in diameter, and it's a relatively young crater. It's only 1.5 billion years old. So again, Theophilus has a pretty prominent central peak. Unfortunately, we're kind of at the point where we can't see it very well because the sun angle there is too high. But if we were looking, say, 2 or 3 days ago, it would cast a very nice shadow. You'd really see the relief of that crater. It's pretty dramatic. All right. And then
Yeah.
continuing on down south here, just wanted to point out one other crater, just to kind of wind things up here. Oops, go east, young man.
That's a very nice looking shot.
Yeah.
Right
This
there.
is
Yeah.
this region is called the Southern Highlands. So the southern half of the moon seems to be much more heavily cratered, a lot more mountains and so on, and it's older terrain. Whereas where all the mare are, the seas, that's where it's smoother and it's been resurfaced by the lava oozing up and filling those basins. So you see another crater here with a very prominent central peak right there. That is the crater Tycho. Tycho is a very young crater. It's perhaps only 100 million years old, which is young in moon time. And it's about 52 miles in diameter. One of the cool things about Tycho is if we wait a couple of more days to where the sun is a little bit higher, Tycho has these long rays, bright rays extending out in all directions. And that's caused by ejecta. When that impact occurred that produced the Tycho crater, it threw material up into the sky, which then traveled long distances because the moon has weak gravity and no atmosphere. So ejecta, rock and dirt blown out of that crater, traveled huge distances in all directions. And when you look at the moon with a pair of binoculars or a small telescope, especially a couple of days later when the sun angle is a little higher, you can see those rays. They really stand out, and they're all extending in all directions away from the Tycho crater. All right. And then last but not least, coming down here a little bit more, right below Tycho, you see a kind of a round crater with a string of craters inside of it right there. And that's the crater Clavius. Clavius is a really cool thing to image with a telescope and a camera because it has a lot of detail. And this is the perfect time of the month to be imaging it because you got all those nice shadows and everything that really shows the detail. Clavius is a pretty big crater. It's 136 miles in diameter. And the main crater is pretty old. It's almost 4 billion years old, 3.9, 4 billion years old. But you see other craters inside of it, and those are much younger craters. And that's one of the ways that we figure out the ages of things is we see which craters look old and battered and which craters look young and fresh. That gives us a chance to kind of get some relative ages. And then we rely on the samples brought back by the Apollo astronauts to get absolute ages because we can age those samples in the laboratory. We know where they were taken from, and then we can use that to establish the age of craters around it and figure out how old some of these craters are. Okay.
Thanks, Gerald.
Well, that's our tour of the moon.
That's good. How are we doing on humidity, John?
Actually,
We're doing good.
down.
Yeah, it's gone down.
Oh, that's good to hear. All right, glad to hear it. I do see one question that someone has asked, which I figured I would take a shot at answering. Albert, you mentioned that you saw a nice shot of the Rosette Nebula. That's also one of my favorite deep sky objects to look at. The Rosette Nebula, though, is a huge object, and it covers a pretty sizable swath of sky. If we were to point this telescope at the Rosette Nebula, it would be a fraction of one petal of the rosette. It would be a very, very small area and would look nothing like those photographs you've been seeing over the last week or two. It's also a very faint object, and we would have to take fairly lengthy exposure in order to really even begin to see the patterns and the overall shape of that object, such as we'd be able to, given the amount of magnification we get from this telescope. So, not a good target for Nellie, but I'm glad you had a chance to see that because it's a really beautiful object.
All right. Do we have any other questions?
No, actually,
I do see one.
Oh.
Someone just came in from
Oh.
Stephen Schreier. Go ahead, John. You see that one?
no, I didn't. Hang on a second.
Okay.
Oh,
Says
okay.
how deep are some of the moon's craters? And is the gravity on the moon similar to Mars?
Gravity is less. Gravity on the moon is only about 1/6 gravity on the Earth, whereas the gravity on Mars is about 1/3 the Earth's gravity. So you're pretty light on the moon. You're a little bit heavier on Mars, and then you're full weight here on Earth. So,
We can consider the moon about half of what Mars would be, though, based on those numbers.
Right. Yeah, technically it's 38% of Earth's gravity on the moon and 16 point something percent on 38%
The other way.
Mars.
on
Yeah.
Mars and
Yeah.
16%
on the moon.
We knew what you were talking about.
Yeah, I never do, but
Right. All right. Very cool.
all right. So
What's our plan for the next part here?
well, let's see. A couple of things I thought we'd look at. One of which is a planetary nebula. It'd be interesting to see how well it shows up. It's called the
Before you move, there is one request that I missed.
Okay.
Oops.
He wanted us to go to Mare Cognitum.
Oh, okay.
You know where that is?
I got to figure it out. Hang on a second here.
If we do, he can dazzle us with his shocking specialized info.
Oh yeah. His encyclopedic knowledge of the moon.
What is it? Mare Cognitum?
Yeah, Mare Cognitum. Exactly like that.
Would that be?
Actually, unfortunately it's on the other side of the Terminator, so it's
okay. Too dark.
Yeah, too dark.
Ask us in a couple weeks or a few weeks.
Yeah, we're not too far from where it is. Oh, I shouldn't have done that.
Well, now we're really.
Now we're way out.
Wrong button.
You people couldn't hear that, but we could hear the telescope move quite a bit.
It's like, whoa, what was that?
Yeah, see. Now I really messed it up, right? Hey, there we go. All right. So yeah, it's unfortunately it's just to the left there of
It's like right.
Yeah.
Like right over here.
Right in that region right there. Yeah.
All right, maybe next week.
Sorry.
Yeah.
Okay, so anyway, I was thinking we'd go with the clown-faced nebula.
All right.
That's a good one.
All right, so hang on here. I'm going to take us over to Pollux and use that to synchronize.
All right.
So what we're going to do now is move the telescope to a bright star near the object that we want to look at, and make sure that the telescope is accurately pointing. It's probably going to be pretty close. So there's
that's not bad.
Not too bad. Yeah. Yeah, so this is just a way of making sure that the telescope is pointed correctly before we go to an object that is faint and hard to see. All right, here we go. And Richard, you're going to have to do a long exposure to see this.
Yep. I'm going to start with 30 seconds and we'll see how that
Okay.
does.
All right, so let's give it a shot. This is a faint object. It's quite faint, not something you could see with your naked eye. And it's what we call a planetary nebula. There are quite a few planetary nebulae out in space. They are the remnants of dying stars. So this was once a star, possibly similar to our sun. And when it reached the end of its life, it swelled up, became a giant star. It then started losing its outer layers of gas, and over thousands of years, it just blew off the outer layers of gas, exposing the inner part of the star. Eventually, the star, the fusion process, which is what drives the star, that fusion process stopped. Whatever was left of the star collapsed into what's called a white dwarf. Oh,
well, we got some.
Okay.
Movement there.
Yeah, that's because I still had it tracking at the lunar rate.
That's actually pretty interesting. That it was
that much difference.
Yeah. All right. Anyway, I'll grab another frame here.
So what I was referring to there, as far as the tracking, the Earth is rotating, and the rotation of the Earth causes the stars to move across the sky at a certain rate, roughly one complete revolution every 24 hours. The moon also moves across the sky because of the rotation of the Earth, but the moon is also orbiting the Earth. And so the Earth's rotation makes the moon want to go from east to west, but the orbit of the moon around the Earth causes it to want to go from west to east. So it goes east to west much faster than it does.
There we go.
Yeah, that's actually pretty nice.
It is.
So when we're looking at stars or nebula like this, boy, that is a good one. We track at one rate, and if we're looking at the moon, we track at a different rate. So I had it set for the lunar tracking rate, but now we've got it set for the stellar tracking rate, what we call a sidereal rate. So anyway, this is a planetary nebula. This was a star once like our sun. It has reached the end of its life. It has collapsed down to form what's called a white dwarf. White dwarf is a very small but very energetic object. It's maybe only the size of the Earth, whereas the star was once maybe 1 million miles in diameter. It's now shrunk down to 10,000 miles or less. And all of that gas that it was blowing off while it was a giant star, before it became a white dwarf, all that gas that was blown off is surrounding the white dwarf. And it comes off often in fits and starts. So it creates shock waves. And so if you look around the bright center, you can see kind of a fainter shell around it. And then inside, you can see a much denser shell of gas. This is all gas that was blown off of the star during that giant phase, red giant phase, when it was expelling its outer layers of gas. When this happens, the star can easily lose half or more of its mass before it eventually becomes a white dwarf. In fact, if the star, say, had 3 times the original star had 3 times the mass of our sun, it has to lose more than half of its mass in order to become a white dwarf.
Here's a really good question from Dan. How hot is the surface of this white dwarf?
About 30,000 degrees, maybe even a little bit hotter than that. It's very hot.
That's really hot.
What's happened is the star still had a lot of heat. When the fusion stopped, it still had a lot of residual heat, but it collapses down and forms that white dwarf. White dwarf is composed of what we call degenerate matter, which is extremely dense. And it still has all that heat, even though it's not fusing anymore, it still has all that residual heat. And because it's so dense, it takes a long time to dissipate that heat. It can take 1 trillion years for the white dwarf to eventually dissipate all of its heat, and then it becomes what we call a black dwarf. But that can take actually longer than the universe has been around. So you're gonna have to wait a while before you see this white dwarf fade out. Now the gas around it is expanding away from the white dwarf, and eventually it will dissipate into space, probably combine with gas and dust from other dying stars, and maybe form a new star somewhere.
And that will be much, much quicker. It will only take a few tens of thousands of years for that to happen.
Right. And so what you're seeing here is a preview of what will happen to our sun in about 5 or 6 billion years. Our sun will go through a very similar process. It will expand, become more than 100 times its current diameter, and then it will lose its outer layers of gas and eventually collapse down and become a white dwarf. And somebody far out in space will see our sun, 6 billion years from now and say, hey, there's a really cool planetary nebula out there.
Hopefully they won't call it a clown face like
right.
This.
Now you may wonder why it's called a clown face. You can't see it very well with this image here. If Richard were to take a whole bunch of images and process them very carefully, you would see that in that central bright region, there's actually some kind of reddish blotchiness in there, which sort of gives it the appearance of a clown's big red nose. And so that's where the clown face came from. Now, this is very common. Most stars die in this process. So most stars become planetary nebula. They die this very slow process that takes hundreds of thousands of years. But it doesn't happen until the very end of their lives.
We have another question here that I'm not familiar with. Michael asks, is this Cleopatra's Eye Nebula? I've never heard it mentioned that way.
I've never heard it referred to as that, but I could be wrong.
See if I can look that up.
Why don't you look that one up, see if it's the same object. A lot, there are many planetary nebulas, and there's dozens of bright ones like this, and they get rather poetic with the names. And
now this one does have another name, but NASA is discouraging us from using it. A little bit of politically incorrect, so we'll just call it the Clown Face Nebula.
The name that cannot be said nebula.
Yes. Now you notice the greenish color. This star was probably at the point in its life where it was producing oxygen at its core. It had gone past the point of fusing hydrogen into helium. It was now fusing helium into carbon and into oxygen. And although most of the gas coming off the star was hydrogen, there was some oxygen coming off the star as well. Oxygen, when it's ionized, glows in a very, very bright greenish blue, kind of turquoise color. And that's what you're seeing. It's not the dominant gas. There's actually a lot more hydrogen surrounding the star than there is oxygen. But because oxygen glows so brightly when it's hit by ultraviolet radiation from the white dwarf, it seems to be the dominant gas. And we see that with a lot of planetary nebulae. They have this kind of greenish bluish color to them, which is caused by ionized oxygen.
Now, this also has a Messier number, right?
No,
it does not.
No,
got it. Okay, so I can't answer. I wanted to answer Stephen's question of when it was discovered or cataloged. And I was trying to remember if this had a Messier number associated with it. So now I have no idea what the answer is.
No, sometime in the 19th century.
Got it. Okay.
18th century.
So it would have been maybe Herschel who
Yeah,
discovered it rather than Messier.
This has an NGC number. It's NGC 2392.
Got it. Okay.
I did also find Cleopatra's Eye, and it is a different nebula. It's NGC 1535.
Okay.
But there are a lot of planetary nebula out there. You may have heard of the Ring Nebula, which is in the constellation Lyra. The Ring Nebula is a planetary nebula.
Well, Dave Shaw got back to us on this. He says it was discovered in 1787. David, do you have a discoverer associated with that, or just the date?
Really, that far back? No?
Yeah, that's something, isn't it? Anyway, we'll wait for David.
What year was that?
Time back in 1787. He said.
That's interesting because this.
William Herschel. There we go.
It's interesting because this NGC 1535, the Cleopatra's Eye Nebula, was also discovered by Herschel in 1785, just a couple years earlier than that.
There we go. That's really interesting.
It's very similar to the Clown Face Nebula.
Well, it kind of tells you what range of magnitudes and resolution he was able to get with his telescope.
Yeah, he had a big telescope.
Yeah, and he was able to pick up this particular classification of objects, whereas Messier may have been having a harder time with objects of this size.
Yeah,
it's interesting how Herschel did this. Today we would take the telescope and we would scan back and forth across the sky looking for things. Herschel used a different approach. Herschel would point his telescope at a certain azimuth above the ground, so a certain angle above the horizon, and he would just park it there. And then he would sit at the eyepiece of the telescope, and as things would drift by because of the rotation of the Earth, he's not correcting for the rotation of the Earth, so he's just letting the sky drift by in the field of view of his telescope. And his sister, Caroline, would sit with him. And as he spotted an object like this, he would very quickly describe it to her. And they would note the time of the night at which they saw it. And from that, they could then determine the coordinates of the object in the sky. And Herschel discovered all kinds of faint fuzzies like this using that technique. And you can just imagine the tremendous amount of patience and perseverance that it would take to do something like that. I mean, just sitting there night after night, just watching the sky drift by in your telescope and hoping that you see something unusual.
Wow, a lot of hot tea involved.
Yeah, right. So what time is it? Oh, it's about 9:40. You know what?
9:40. It's galaxy time.
I think it's galaxy time. How about, shall we go for M65?
Sounds good to me.
All right.
Let's let this shot complete here, and then we'll move on to the next.
Okay.
Next
I'm gonna use Regulus as a. That's not Regulus.
Okay. So
okay, you ready?
Yeah, let's go back to frame and focus here and see if we could sync on Regulus.
Well, I'd like to, but I'm having a little trouble here.
Really?
Uh-oh.
Yeah, what's going on here?
We were having some technical issues tonight, folks, and we thought we solved them all before we started, but...
Okay. Hopefully I'm going back to Pollux.
There we go. Yep.
That looks good.
Okay. All right.
Very close, anyway.
Yeah.
Wow,
okay, that's close enough for government work, right?
Most definitely.
Okay. Now let's see if I can go here. Okay, there we go. And will it let me go to Regulus? Yes. All right. Now we're going cooking with gas here. So this time of the year, especially as we get into spring, is often called galaxy season because of the position of the Earth in its orbit around the sun, and because of the tip of the Earth's orbital plane relative to the galaxy. This is the time of the year when it's easiest to see a lot of other galaxies. And so we often call this galaxy season. So this is the star Regulus. You notice it has a little bit of a bluish color. Bluish color means it's a hot star. All right. Okay, so
Mary says it's cooking with plasma.
all right, so we're going to go to M65.
All right. And so the M designation, which is what I had mentioned earlier, stands incorrectly, stands for Charles Messier. And Messier was an astronomer from the 1700s who put together a very well-known and still fun to follow catalog of bright astronomical objects. He was basically looking for comets and was cataloging everything that he decided was not a comet but was unusual. And there's a collection of galaxies, globular clusters, open clusters, even and planetary nebula, and even some double star in his catalog. And it's a really the first catalog effort from Europe during that time period, anyhow, that has been made famous over time, and that students of astronomy still use today.
Okay, I think you're probably going to need at least a 30-second exposure, Richard.
Okay, you ready?
On M65, yes.
Okay, let's just go for the same exposure we were doing.
So
we're looking at our previous object here and won't show the new one until it's completed the shot.
So like I say, this is galaxy season, and we're pointing now in the direction of the constellation Leo, the lion. And there are quite a few galaxies in Leo, and some of them seem to be kind of clustered together. So there's actually a group of galaxies very close to the one we're going to be looking at. And these are all galaxies that are roughly the same distance away. And they look like they're clustered together. That's actually very common for galaxies to be clustered together. We see quite a few of them. I see something.
Yeah, I see something, but it's not what I'm expecting to see. But that does kind of look like the core of a galaxy.
Yeah.
But it's probably demanding a...
What ISO are you at?
I'm at 1600. I'm going to go up from that, and I'm going to also add another 20 seconds. We'll see what happens. There we go. It's you can see that it's there, Gerald, but it's just kind of on the dim side right now. So let's see what this next shot does.
So that's the 30-second shot, right?
Yeah. I think the next one should be better. Yeah, you can almost get something now.
Oh, there you go. There you go.
Yeah. And that's still the 30-second shot. Next one should be better. We were just zoomed in, so it wasn't picking up the contrast.
Oh.
Okay, stand by.
There you go.
There we go.
There's a galaxy.
Yep.
All right, so this is M65. M65 is about 35 million light years away. And you can just barely make out, when you zoom in, you can just barely make out its spiral structure.
Yeah, you get a little bit of spiral here, and you definitely see it here. It's a little bit of a challenge, I think, for the viewers remotely, but I could try to stretch it a bit.
Yeah, by the time it gets to Facebook, it fades a bit, so
Yeah.
you can still see it there, though.
There we go.
Yeah, what do we do here?
Our humidity is holding nicely. It's down to 79.
Okay, well,
I think we'll make it the next 10 minutes.
Yeah. So after we do this one, Richard, this is kind of a faint one. I think we should do one that we know is going to look nice and bright and cool, and that's M51.
Oh,
yeah. Good choice. Yeah, we'll just let this one go and okay, let's move on to the next one.
Okay, all right. So we'll do a little galaxy exploring here. I'm going to go ahead and sync on Arcturus. What?
Same issue.
Is Arcturus visible? I think it's too low.
Oh, yeah, it is.
Yeah.
Yeah.
Yeah. In fact, I can't even see it.
Yeah, you'll have to do a dipper star.
Yep. What I got to do is find the dipper first.
Come on, don't you know the song?
Yeah, let's see here.
Just look for those bears.
Jasper asked a good question. Can you tell if it's a star or if it's a galaxy without using the Hubble Space Telescope image? Absolutely. When you're looking at a galaxy visually through a telescope, even a small telescope, it's more smudge-like. You'll see the core of the galaxy, which might appear somewhat star-like, but definitely fuzzier. But you'll usually, if you're looking at something magnitude 10 or brighter, also see the halo around that star, or if it's a really bright galaxy like magnitude 8 or brighter, you'll see the spiral arms. So most definitely.
You usually won't see that when you're just looking live through the telescope, though. You need to take a photograph most of the time.
Are you in live view now?
I am in live view now.
Why don't you switch to live view?
I am in live view.
Okay.
Yeah.
We should be seeing a star here.
Let me make sure we're not zoomed in. We're not. Okay, let's take a look through the Finder if we can. That's going to be tough.
Yeah, it's kind of out of your reach there.
Yeah, it sure is.
I might be able to get to it.
We made a pretty big move across the sky, and when we do that, quite often the telescope control system doesn't get it quite right. Since we have such a small field of view, we can be extremely close, but not quite there. So what we do is John's going to go over and he's going to look through the finder scope, and he's going to kind of adjust it a little bit to try to bring the star into field of view here so we can synchronize it before going to our next target, which you'll really like.
Yeah, Michael mentioned the EV scope, and he's right. The EV scope is a cool instrument. It's pretty new.
Oops, right there, John. Right there. Yep,
got it?
yep.
There it is. The EV scope takes a whole series of images and stacks them and shows them as a color image to the viewer. It's controllable with an iPad, an iPhone, Android device, and they're quite good. It works best with very bright galaxies.
Are you still on live mode?
Yeah, I am. It's there.
Yeah,
you just have to move up a little bit.
Yeah, I wish I could, but I can't seem to get it to move.
Huh. Well, that's strange.
Is it not moving the telescope, or is it?
Yeah, the control pad is not moving the telescope.
Let's see if they're both doing that.
Bear with us, folks. Technical difficulties. So you want to do set and south.
Yeah, we're not getting any motion here either. I think we do have an electronics issue. Okay, watch your head. Yeah, we're not getting any motion.
We'll stand by here.
So anyway, yeah. So the EV scope is a really cool instrument, and it's like a combination of a telescope and a camera, and you're able to do some pretty neat stuff with it. So, yeah, if you've had a chance to look through one, that's quite cool.
Are you moving it, John? Because I'm not seeing anything here in the field of view. I think there's a camera problem, Richard.
No, I'm seeing the star.
Yeah, but he's moving it, and it's not moving on your screen.
Oh, I see what you're telling me. Okay, stand by. It's actually a Windows problem.
No.
Yeah, it looks like the camera got disconnected and it did something. All right.
Did you accidentally bump one of the cables and pull it out?
That's what it's kind of acting like. All right.
So there was nothing wrong with the telescope. It was the camera that was the problem.
All right. So at this point, the camera's back, but we're not seeing the star.
Not seeing any display on the camera.
Huh. Yeah. Well, let's just.
Yep, there's something.
Well, I just turned it off. Okay.
So you got the three stooges up here operating the telescope and the camera.
That's right. You bet.
Believe it or not, this kind of stuff happens all the time, even with professional astronomers.
Okay, so I am definitely reconnected to the camera, and we are. It's not. We might have moved off the position of the star, though. There it is. Gerald, do you see it?
No, you've got it. You don't have it showing on the screen.
Yeah, it's on the screen, lower right side.
No, it's not.
It's right on my screen. Oh, I don't have it on the shared screen. Okay.
Yeah.
Got it. Now I know what you mean. Bear with me.
There really is a really cool galaxy that we're eventually going to show you, folks.
Yeah. There you go. Okay.
Aha. Okay, I see it down at the bottom. And I am making it move.
You press enough buttons often enough and
Yeah.
in rapid succession, eventually it does the right thing. It's the monkey and the typewriter theory.
Okay, I am now going to slew to M51, the Whirlpool Galaxy. And
Okay.
Richard, probably a 30-second exposure.
Yeah.
So M51 is one of the most frequently photographed galaxies because it's fairly bright, easy to see, and because it has a very unusual appearance to it.
You'll see that hopefully real soon here.
Yeah, M51 is about 15 million light years away, so it's farther than the Andromeda Galaxy by quite a bit. But M51 is actually two galaxies. So there's going to be a big one and a small one, and you'll see that they're feeding into each other. Any second now.
Okay.
Might need a longer exposure.
Yeah, we will bump up in a second. I just want to see what we've got here.
Always funny to deal with this because when I use my astronomical CCD camera, this thing just pops right out. I can do like a 10-second exposure and see all kinds of detail in it. But astronomical CCD cameras are much more sensitive than a digital SLR camera, which is what we're using for tonight for this exercise. You can see the bright central core of the galaxy.
Yeah, and a little bit of the spiral arms, but probably
Right,
you guys
right.
aren't seeing that out in Facebook land.
Now, it's not unusual for galaxies to merge. In fact, in about 3 billion years or so, the Milky Way galaxy and the Andromeda galaxy will begin merging with each other. Milky Way and galaxy and the Andromeda galaxy are drifting towards each other. I say drifting, and it's actually very high velocity. It's about 300 kilometers per second is how fast we're moving toward each other. There you go.
Yep, let me get the contrast right.
Yeah, we're losing detail.
Yeah, there we go.
That's looking better.
There you go. So you can see the large spiral galaxy, and what you can't see right at the top of the frame, you can see kind of a bright fuzzy patch. That's the other galaxy. And if you look
right
careful,
here.
right,
I see.
right.
Yeah, I was wondering where it was, and now I realize it's off the field of view.
Right. Yeah. So what you can see very faintly is a kind of a streamer going from that smaller galaxy at the top of the frame towards the bigger galaxy.
Usually in a case like this, we would probably rotate the camera 90 degrees.
Right.
And then we'd be able to see them both.
We'll probably, over the next couple of weeks, as this object gets higher in the sky, we'll take several images of it. And maybe Richard can take quite a few and stack them together and produce a really nice image. Yeah, there you go.
I just had to get the right the little grid they give you in this software is a little odd.
Yeah. So you can definitely see spiral arms in the galaxy. You can see some dark lanes. Those are clouds of gas and dust. It's a very typical spiral galaxy appearance. And like I say, it's slowly drawing in material from that other smaller galaxy.
Nice. So when galaxies collide, it's not like two trucks colliding.
Yeah.
When stars collide, it's more like two trucks colliding. But when galaxies collide, it's a very ephemeral event. And stars are so far apart from one another, even during a galactic collision, that everything just passes by one another, right? It's like two crowds of people merging that are walking in opposite directions, but have maybe 10 feet of space in between each person. And you can imagine that the two crowds would just pass through one another. And that's kind of what a galactic collision is like.
Not that they wouldn't affect each other, though.
They would affect each other, and that's what the streamers are.
Right.
Yeah, I mean, some people in crowd number one will say, "Hey, I'd rather be with crowd number two," and they'll go ahead and change direction, and that's kind of what's happening.
Brandon has a question. I think it says a whirlpool right into a black hole? Question mark. I'm not sure what that means.
Well, there is a black hole at the center of the galaxy.
Yeah, that's true.
Pretty big black hole, actually. What we call a supermassive black hole. And the smaller one also has a black hole. It's a smaller black hole. And when the two galaxies eventually merge, the black holes will merge, producing an even bigger black hole at the center of the merged galaxy. But that's, billions of years to go before all that happens. Well, we're well past 10 o'clock here. So, if you have any other last minute questions you want to shoot at us, go ahead and do that. We also want to encourage you to hit that donate button. We do rely on your financial support to help us out while we're closed for the pandemic. And you can donate on the Facebook page, or you can go to Chabot's website, the chabotspace.org website, and you'll see a donate button at the top of the page there. We want to encourage you to help us out if you can. And we'll continue here for a few more minutes.
Stephen asked, can Nellie image a deep field space image similar to Hubble? Well, we got a couple of things going against us for that. Number one is we're in the middle of Oakland, which, we love Oakland, but it's got a lot of bright lights. So it's very hard for us to pick out those magnitude, 20 galaxies that the Hubble seems to be able to pick up like popcorn, right?
Yeah,
and so it's the light pollution is a big factor. The Hubble also is in outer space, so by being in outer space, it doesn't get any of the atmospheric distortions or other distortions that come into play on a terrestrial instrument. But we could pick up a lot of very dim and numerous galaxies given enough time with a sensitive camera. Right. We usually don't use Nellie that way, but there's nothing theoretically preventing us from doing so.
A couple other disadvantages compared to the Hubble. The Hubble Space Telescope mirror is considerably larger than ours. Our mirror is 3 feet in diameter. The Hubble mirror is 8 feet in diameter. Uh-huh. And also, those deep field images that you see, those are very long exposures, like 30 plus hours. And for us, that would require...
That's nearly impossible, right?
Yeah. We can't point at something for 30 hours.
Yeah.
The sun gets in the way.
Well, the way you do that with a terrestrial instrument is you take images throughout the night, and then you reposition the telescope the next night to the same place you were shooting and shoot again, and keep doing
Exactly.
that night after night until you've stacked up enough images. The Hubble, though, is able to do, because it's in space and because it has this advanced gyro correction mechanism. Whereas on Earth, we might be taking, 5-minute exposures or 10-minute exposures. The Hubble can actually take really, really long exposures and go really deep in a way that is much more difficult on a terrestrial instrument. Oh, let's see what else we got here.
All right.
I think that's it.
Okay. Well, thank you, everyone. Hope you enjoyed the show tonight.
Yeah,
We will do this again next Saturday night. And we may have a special treat for you next Saturday night. There is a big asteroid that's going to come sort of close to the Earth. And we're going to try to image it next Saturday night. You may be able to see it moving across the field of view of the telescope. So something to look forward to.
All right. Thanks for putting up with our technical problems. We'll try to leave those at home next week.
Yeah, really.
Yeah.
We can blame it on the cold weather.
Yeah, that's a good choice. We'll do that. All right. Good night, everybody. Stay well and enjoy your week.
Good night, everybody.
Right.
There we go.